In this video then, I'm going to be running through some Bond enthalpy calculations. So these are very similar to GCSE level bond energy calculations. And at A level, it doesn't get that much harder. It's very much the same ideas at GCSE. So if you want to work out the delta H for a reaction, it's simply the sum of the reactants minus the products, okay? And that's the bond energies. It's the same as GCSE. There's very little that actually changes. So just to prove it to you, these are a couple of questions from A-level papers. So explain in terms of bond breaking and bond forming why a reaction can be exothermic. So to answer this question, bit of exam technique here because you always answer it in the same way. Okay, if a reaction is exothermic, then all you've got to write is more energy is released by bond formation. Okay, so you've got more energy coming out by bond formation than what you are putting in to break them. Okay, then what is used to break them? And that's it. There's nothing more to it than that, but it does require a bit of exam technique because you have to talk about the energy being released by bond formation, the energy being used up to break the bonds, and the fact that you're getting more energy back from the formation of the bonds than what you had to put in to break them originally. So again, for a one marker, there's just one sentence. It's something you can just commit to memory. And of course, the opposite holds true. If a reaction is endothermic, then more energy is required to break the bonds than is what you get back by making them. So nice and straightforward. What I want to get onto then is looking at bond energy questions. Now, back at GCSE, a lot of the bond energy questions were all about calculating delta H for a given reaction. At A level, this doesn't really happen as much. We tend to get, essentially, calculate a missing bond. So in this given reaction up here, so this is the complete combustion of ethene, and it tells you that the delta H is minus 1318. So let's just put that here. Delta H is minus 1318 kilojoules per mole, and it's the combustion of ethene to form CO2 and H2O. So best way to do this is to draw them out. Okay, if you really struggle to visualize, then draw it out because it shows you the bonds. If you draw the displayed formula, you have the bonds right there. Okay, and they can be very useful. So plus O2 goes to COO, so carbon dioxide, and water. Nice and straightforward. And of course the balancing numbers are there as well. So we've got 3, 2, 2 there. So we need 3 oxygens, 2 carbon dioxide, and 2 waters. Now, in order to calculate the C to C bond, it's a bit like a strange question because normally you calculate delta H, but now you've got to calculate the door bond. But thankfully, it's the same process. Okay, delta H is still reactants minus products, only we know what delta H is now. So delta H, so minus 3138 equals all of the reactant bonds minus the product bonds, and we can fill in most of these numbers. Now, we can't fill in the carbon-carbon double bond, we don't know what that is, so it equals X, but we can fill in all the rest, so we'll put it all in brackets. So this is the reactants. So we've got 1 carbon-carbon double bond, and we've got 4 carbon to hydrogen bonds, so it's 4 times 413 plus, and we've got an oxygen double bond here, which is 498. We have 3 moles of oxygen, so 3 times 498. Brilliant. All of that added together minus all of this added together. So we've got 2 lots of CO2. So each CO2 has 2 carbon oxygen double bonds, and there's 2 lots of them, so it's 4 times 805 plus, okay, same thing again here, we've got 2 OH bonds and there's 4 of them, so we've got 2 water molecules, and we've got 2 lots of OH per molecule, so 4 of those as well, times 464. So that's how it works at the moment. we just need to simplify this. Okay, and we can do so. So I'll simplify the right hand side first. So 4 times 805 plus 4 times 464. It's a big number, so this is 5076. So this is 5076. And on the other side, I'm going to simplify everything apart from the x. So 4 times 413 plus 3 times 498. Okay, gives you 3146. So x plus 3146 minus 5067 equals minus 1318. And now it becomes a straightforward game of rearranging equations. So all we need to do to rearrange this equation is take my plus 3146 onto the other side. So let's just take this. So minus 1318 minus 3146, and then we take minus 5076 and move it over. So plus 5076 equals x. And if we plug all that into a calculator, so 116 plus 5076, we get 612, which is the correct answer. And that's it. Okay, so once again, in terms of exam technique, this is a very straightforward process. You put in all the numbers you know, simplify as much as possible. So take, these brackets here, simplify down so you end up with as few numbers to work with as possible, and then it becomes a straightforward rearrangement to get 612. Okay, remember, of course, that this number must be positive, so whenever you report an average bond enthalpy, notice all of them are positive numbers. So even if you get a negative number, so you can do this sum, sort of the wrong way around, and work out minus x and get minus 612, but your answer should always be positive. So we can, basically a bit like Q equals MC delta T, when you've always got to make it negative. This, you've always got to make it positive. But realistically, if you do the correct rearrangement, you should get a positive number anyway. Right. Again, another similar question here. I'm just going to go through one more just to show you, how straightforward these can be. So again, average bond enthalpy. Okay, it's the average amount of energy required to break a mole of a certain type of bond. So in terms of the mark scheme answers, it might seem as though it's a bit of a weird 2 marks, but it really is just for saying, 1 mole of bonds. 1 mole of bonds gets you the first mark. So an energy required. Okay, to break. Okay, so essentially, it's the energy required to break 1 mole of bonds. So 1 mole of bonds gets you a mark, and the second mark is for saying it's the amount of energy required to break them, or just break them. I think the mark scheme even says. So it's very, very straightforward for 2 marks. Again, 3 lines, you need literally about 8 words. So your 1 mole of bonds is the energy required to break 1 mole of bonds. That's it. Okay, or a certain type of bond if you want to be more specific. So let's get into the bond enthalpy calculation then. So again, it's similar to last time. They've given us delta H, and we're trying to work out the bond in carbon monoxide this time. So they've already balanced the equation. In fact, it's quite a straightforward balanced equation. So delta H, so plus 210 equals the reactants minus the product. So in methane, CH4, so I'll just draw it for you there. It's oh dear, that's a terrible line. Why did it go there? Yeah, CH4. There's 4 carbon hydrogen bonds, so that's what we put down. So 4 times carbon hydrogen, 413. Again, the numbers are quite familiar from last time. Plus we've got H2O, so again we've got 2 OH bonds, so 2 times 464. And that's the first section, minus X. Okay, so minus X plus 3 lots of hydrogens. So you've got H2, which is a single bond, times 3. So 4, 3, 6 plus. In fact, I'm going to write this a bit easier because in reality, so I'm just going to rewrite this a little bit because instead of doing x plus, you can just do the minus. Okay, you're just subtracting everything. So it's reactants minus product. So minus x minus 436 times 3. Okay, so that should give you the right amount, or it's the same thing. It's just x plus minus. It's the same thing. If I add it together, it doesn't matter. So just to highlight what I mean here, I'm simplifying it because if I add, if I do in brackets, for example, x plus minus 436.3, sorry, times 3, it's just the same as just doing minus. So we'll keep it like this to make it, a bit more straightforward and to separate x out from a bracket. So we'll just put that in brackets for now. So again, we'll simplify this down, okay, as we did before. So on the left-hand side, it's very, very easy. So 4 times, what am I on about? That's not a minus number, is it? Oh my God. Yeah, forget what I just said about any of that crap. Honestly, I don't know what I'm on about at this moment in time. I'm probably just confusing everyone here, but we're just going to pretend I didn't say anything I just said. Okay, we're going to make this very easy, okay? I'm going to go back, I'm going to do it as I was going to do it the first time, and I'm just going to stop wasting everyone's time. So x plus 436 times 3. There we go. We'll just leave it like that and then sort it out later. Right. In terms of the left-hand side then, we can sort that out very, very quickly. 4 times 413 is 1652 plus 2 times 464 is 2580. That's straightforward enough. 2580. And then we've got to minus everything else. So this is where I'm going to separate out the bracket. So 2580 minus, okay, x minus 436 times 3. Okay, I'm doing that because I want to separate x from the bracket, and it's a pain in the backside because I don't know what these numbers are. So I'm just going to subtract it. I'm going to minus it at this point. So that equals plus 210. So I'm going to make it negative. It just separates it out. Again, because this is exothermic, because it's bonds being formed, this value is going to be negative anyway. I'm going to have to subtract it regardless. So how do we solve from here? Then right, first things first, I've got a minus x. Now, we don't want minus x, we want plus x. So that means I'm going to move my minus x over to the other side to make plus x. And because I've already got plus 210 here, I'm just going to move plus 210 over to the other side. So that means x equals 2580 minus 436 times 3 minus 210. And if we bang that into the calculator nice and quickly, so 2580 minus 436 times 3 minus 210, we end up with 1062, which is the correct answer. And again, positive number because obviously it's a bond enthalpy, so it's reported as positive. It's going to be a very big number because remember the carbon monoxide bond is a triple bond, so it's going to be very, very strong. So yeah, essentially because it's reactants minus products, everything on the right hand side can be negative. So rather than trying to work out this horrible bracket, we can just do minus x minus 436 times 3, remove the x to the other side and put it in. Again, mathematically there's a number of ways to rearrange and do this, but it's just about finding a method that works for you. As I've said earlier, taking everything simply, plugging everything and then getting your correct answer is the best way to do it. And again, you didn't have to turn x into the other side, okay? You could have taken 2580 over to the other side, the 436 times 3 over to the side, and worked out minus x, which would have been minus 1062. And as long as you write down positive 1062 on the answer line, you get it right. So, like I say, as long as you realize that the Bond enthalpy must be positive, you can rearrange it however you like in order to calculate the answer. So there you go. There's a few little questions on Bond enthalpy. Hopefully that has not been too confusing there at the end. But in all honesty, it is just about a simple mathematical rearrangement, and there are multiple ways you can represent the same thing. So, like I say, I would always recommend, especially if you've got minus x's, just do minus, just minus everything individually. It works exactly the same as sticking it in brackets, it's just easier to do the rearrangement, because sometimes the rearrangements can cause problems because people are trying to move brackets around, when in fact if you get rid of the brackets it makes it a lot easier.